Okay, so look for there's a new live that should have popped up on the channel. I will kill the one that says upcoming. It says live. It says we're live. Okay, we should be live. Almost says it's up. I'm waiting for Mr. Blodgett says, glad you have, he says, you have grit and follow structure. You got it. Absolutely. Yay. Wow. Wes is here on YouTube. Kevin's on YouTube. Welcome aboard. Okay. Happy Sunday. It is 13:11 on the East Coast. And this is the PFG, IG, and YouTube live. Welcome. If you're just joining us, it's hot and humid weather, hot, t-shirt, bright sun, not good. Okay, we got through that. So today we're going to talk about grinding wheels. Now, I have to give you a disclaimer, and that disclaimer is I am speaking to you as a student of grinding. My knowledge in grinding is narrow, and I work to get it wider and understand more things and be a good student. So I'm not coming to you as a master of grinding who has been doing this for 30 years. So, take what I say in the manner in which it's offered. What I do have to offer, from my perspective, is the analogies I created in my head so that I could understand what's going on in grinding. I think that's what I bring to the table. And the same thing happened in my profession of being an antenna designer and an engineer, is that let's take something complicated and simplify it into models that we could work with. And the models are not perfect, but they will get you so far down the road as to be extremely useful. And that's what we're doing today, and that's where we're coming from. Okay, so as long as we could all shake our heads up and down and agree to that, we can all be friends. So if you're on Instagram and you have questions and you have the question button down there on your screen, please use it. And if you have questions and you don't have that button, or you're on YouTube, go ahead and throw it in the chat, and we'll deal with it. So yesterday was I think Friday was a day of grinding. Yesterday I had half a day of grinding, and today I did all the packaging to get stuff out the door, and that was all excellent. So we might as well jump into it. The things I didn't understand, the things I didn't understand about grinding when I started, they fill books with. But grinding wheels were kind of a mystery, and in a lot of cases they still are. And I keep on asking myself, why is that? So if I said to you, I think everybody here who is a machinist, if I said to you, list the different types of end mills, and please explain what each end mill is for. What are the strengths and weaknesses, and where would you use it, where would you not use it? I think everybody would be pretty reasonably comfortable. And the beauty of an end mill is you look at the thing and you can see the cutting edge, and when it cuts a chip and goes flying off into your shoe, you can see the chip. Okay, it's all very visible. Problem with grinding is you can't see that because it's happening on a microscopic level. It's the same process as milling, and somebody's going to yell at me about that, but you're taking a chip, and you just can't see it. So as soon as you can't see something, it becomes voodoo. So let's talk a little bit about why, what multiplies the voodoo, Oh, a chip in your sock is just the worst thing. Indiana Jones says he has a chip in his sock right now. I understand. I think I have a chip in my thumb. I was milling some of this mild steel on the Bridgeport, and I was going too slow, so I was making these needles, these very fine needles, and then I tried to clean up afterwards, and yeah, I think I got one of those in my thumb, and I can't see it. Yeah, yeah. Well, Dan says I heard there are a lot more processes to it than just cutting. Well, there are. That's the problem. We have to just simplify a little bit. So I picked up my little Norton grinding handbook. Hey Nick, welcome aboard. Don't worry, you didn't miss anything. I went up to the office yesterday. Yeah, yeah. Foxburg Fabric Problem says, bury the cutter and let it eat. Try not to track them in the house. So big chips are easy to clean up. They're easy to see. It's the little ones that are deadly. Hey, Ugly Skull. So I went upstairs yesterday, and I found this little Norton grinding handbook, copyright 1947, that a buddy of mine gave me, and it's the cutest little book, and it's directly from Norton, and nothing's changed except that some of the wheel types have been modernized, and we have some new composite wheels, which we'll talk about later. But there was a page in there, and I recognize on Instagram this is going to be backwards, but there's a page in there which I've posted before, which is the grinding wheel markings and how to interpret the grinding wheel markings. Okay, so if you look at it, it's got a couple of sections on it. It's got, abrasive type, okay, grain size, grade, structure, bond, and then some proprietary Norton information. Now, if you look at this closely, you'll see that if we just look at the first couple of columns, that there's 7 types of abrasives. Now, we don't have 7 types of abrasives that we're dealing with typically. But those first 3 letters on the wheel, 32A, 38A, that's the type of abrasive. So they've got 7 of them here. And then when you look at grain size, there are 26 grain sizes. Now, I recognize not all of them are actually getting turned into wheels, but 26 grain sizes. Then there's 28 grades. Okay, the grade is what we're going to call friability. Okay, and we'll talk about that. And then the structure, and we don't know how many structures there are. There's at least 2. I think we could agree that there's at least 2. And then there's the bond type. And again, here we're generally going to talk about in typical wheels made for steel, there's one bond type. When we get into the diamond and stuff, there's multiple bond types. So if we just do a little bit of math here, remember, this is 1947. So this is 7 times 26 times 28. And I think we can agree that there's going to be at least 2 different kinds of structures. That's 10,000 combinations. 10,000 combinations in 1947 of a wheel that you could pick up. Now, they didn't fill out that whole chart. There aren't really 10,000 types of wheels, but there's a lot of types of wheels. So when we walk up to a grinding machine, a grinder, surface grinder, or its variants, and we look at it and we say, this is really simple. You spin the wheel, and remember, in the old days, they did not generally control the speed of the wheel. Now we could just dial it in, and it goes up and down. The table goes back and forth, and the wheel can go in and out, and you're done. How simple can you get? I mean, yeah. And now you have to pick which one of 10,000 types of wheels you're going to use. That has nothing to do with, it has nothing to do with how you're going to dress the wheel, how you're going to hold the wheel, how you're going to balance the wheel. We didn't even talk about what speed your table's running at. And by the way, if you're grinding and you don't think that matters, you're wrong. It matters. So all of these variables are hidden from the casual observer, and this is what gets really confusing. And we talk about the white wheel, you know, the 46I or H or J, as being, you know, baby's first wheel. But seriously, you have to start somewhere and you have to simplify it. So we're going to break down what all these terms mean. We're going to talk about abrasive types. We're going to talk about, you know, grain size or grit size, grade or friability, which is there. Try to do this in the mirror. And we're going to talk about structure. So let's start with, I have notes, I really do. Let's start with wheel safety, okay? Because if, and Mr. Foxberg, I know, has shown that he's sorting out hundreds of wheels that he got new old stock that is going to be available. So he knows this already. When you pick up one of these wheels, you don't know its history. Even if it's a brand new wheel that got shipped to you from your supplier in its single wheel packaging, which is what I like, you don't know its history. So you have to do a couple of things. The most important thing to do is ring the wheel. You've probably heard this before, but I'm going to demonstrate it. So let me grab one. And here it is, baby's first wheel, okay? This is a 46H. The full designation on this guy is 38A, which is the basic Norton white wheel. 46, that's the grit size. We'll talk about that. H, which is the grade. In our case, we're going to call it friability. And VBE, vitrified, and where's the B? Vitrified, and then BE is proprietary. Okay, so the way you ring, you pick up this wheel, and before you mount it on a hub, which we're not going to get into in too much detail, we're going to ring it. Now, the nice thing is we have some good, some good audio here. So you ready? Do you hear the ring? Sounds pretty good. And then we rotate it 90 degrees, do it again. Nice ring. So I believe that this wheel is solid. There's no cracks in it. If you hit it like that and it goes thud with a dull thud, that wheel is about to break apart if it's not already broken. Okay, there's a crack hidden in it. So we're starting with a wheel that we've rung. That's rule number one. Rule number two, when you go to mount this on your hub, this piece of cardboard and this piece of cardboard need to be there. They're called blotters. And I think I showed this before. I had some spare blotters, very old Norton blotters, and they were 17 thousandths of an inch thick, and they were basically like a manila envelope type material, nothing fancy. But when that hardened steel, you have this ground flat, is it flat? Is it really flat? You have this ground flat hardened steel clamp that's going on there, and you got these extremely hard little points. The blotter gives those points a place to go and evens out some of that stress. So even though it's a piece of cardboard, it's pretty important. And then when you go to torque your wheel down on your adapter, give it a good amount of torque. I'm not going to get into that in detail, but you should give it several deci-ugs. That's a torque value. Okay. When you first start up the wheel, and usually most of the time, do not be in the plane of the wheel. Where if the wheel's spinning like this, I don't want to stand here. I want to stand here. Okay. So if the wheel explodes, it's going to explode into that plane. Once that wheel has spun up for a little while, you can trust it, and then make sure you never smack it with anything. So wheel safety is very important, and the amount of energy in a wheel that weighs, pound and a half, spinning at 3,600 RPM is enormous. I think I told the story before, but when I was in school doing high-speed photography, and Dan, you know where I was standing when I did this, in the strobe lab, we would do this exercise where we took a round, about this size actually, a round piece of newspaper on a spindle, clamped on the spindle with a motor, and we'd spin that sucker up and slowly raise the RPM of that motor. And when it hit the magic value, that piece of newspaper would explode, and we would take a picture of the newspaper exploding. The pictures are super cool. The sound of that newspaper exploding caused everybody to require a change of garment. It was amazing. Yes, so Stefan's grinder stepped to the side. If you ask Stefan, he would say the exact same thing. That his grinder, which is super cool, is designed to spin so he can watch the work. Now it's shooting the sparks away from him, but he is in the plane of the wheel in the operator's position. So when he's first mounting those wheels, he's getting out of the operating position and let that thing spin up, make sure it's going to be safe. Okay? We're not going to talk a lot about balancing. You have to balance and you have to dress. Balancing and truing and dressing, all important. But from a safety standpoint, once we've got to this point, the wheel is mounted, okay? And we could relax a little bit. Indiana John says it wouldn't be a bad idea to put a board over the mag chuck when spinning a wheel for the first time. That's a really super good idea, because if that wheel does let go and shoots a projectile into your mag chuck, you just made yourself, 4 hours of work. So that's a good idea. I like that. Also, do I have to tell you to wear your safety squints? Okay. No joke. Make sure you're wearing safety glasses. With all the safety nonsense out of the way, and this is not safety stuff you could ignore. You really do have to pay attention to this stuff. You've got a wheel mounted. So let's talk a little about what this wheel is made out of. Okay. The first most important thing, do you think it's necessary to use a blotter for a thin cutoff wheel? It depends. I'm going to default to saying yes, but I don't have a ton of experience with thin cutoff wheels. And if you're talking about one of the cutoff wheels that has a fibrous structure that is got the grit embedded in the fibrous structure, then the answer to that is you probably can get away without it because the fibrous structure is behaving like the blotter. But if it's a wheel, if it's a conventional wheel, just thin, it may be more important. Barker Michaela, welcome aboard. So all of our grinding wheels is made up of little grits. So if you imagine grains of sand on the beach, okay, and you scoop up a bunch of grains of sand, that's exactly what this stuff looks like in general. So the question is, how big are the grains? So if you were on the beach and you got out your micrometer as one does on the beach, and you started measuring grains of sand, you could, and you started plotting, you made a histogram, a chart of how big those grains are, you can actually get a bell curve that says on this beach, these grains are usually this size and less frequently bigger and less frequently smaller. So we've just characterized, by the way, for you nerds out there, that's called a probability distribution function, right? So it's most likely to be a certain size, but it's not all exactly perfect. It's a distribution. Almost says for cutoff wheels, you want to use cutoff wheel hubs, which should extend out to the sides of the disc. Don't hold a 7-inch cutoff disc with 2-inch hubs. Thank you, Almost. That was very useful. So the grit has a size. If I took you from the beach on the ocean and we went inland to a lake somewhere and we scooped up some of the stuff at the shore of the lake, which might be volcanic, it might be some other type of rock, and there's a type of rock we call river washed, right? The river is constantly flowing over it. Those might be much bigger. So you would, on average, you'd have it bigger. So we could do the same thing with grits on the wheel, and it's a range. So, for example, 150. This is for diamond particles, but it applies to other particles. If we have a grit size of 150, which I tend to use mostly, that's 122 microns, or 4.8 thousandths of an inch, is the average diameter of those grits. Okay, if we go down to 80 grit, it's about 10 thousandths of an inch average grit size. For a 46 grit wheel, it's going to be, again, a little bigger. So when we have a grinding wheel, the first thing we always talk about on grinding wheels is, hey, what grit is it, right? So that is here, the grain size. And in the case of our actual wheel, which is sitting here, this guy says 38A, that's the type of wheel, 46. So this is 46 grit. 38A says it's aluminum oxide. So if we take the aluminum oxide part of it, does that mean there's other types of abrasives? And the answer is, of course there are. So let me grab a tray here. I got some lunch for us. I'm going to use one of my drawers as a table. All right, so here's one that says it's a 46 grit. Here's another one. Ooh, pretty color. That says it's a 60 grit, 60 grit, which means the particles are smaller. Here's one that's green. And this is a type, oh, there it is, 39C, okay? And this is a 39C 60. So there's a 60 grit, etc. Here's some really old ones. This one says it's a 46, and this one says it's a 46. So I'm just going to pile these up on the table here very carefully. So now that we got size out of the way, we're asking the question is, well, what material is it? So the most common grinding wheel material is aluminum oxide. And aluminum oxide is a very hard material. And I've talked about this before. You'll hear people use terms like garnet or sapphire. Water jet cutting is frequently done with garnet in the water. All of those words boil down to aluminum oxide. They have different grain structures, but they're all aluminum oxide. One of the most common metal in the crust of the earth is aluminum. It's a extremely common material. So it's no shock that aluminum oxide is our number one type of grit. But you guys are no doubt aware of silicon carbide, okay? And this actually is not a silicon carbide wheel. Let me grab a silicon carbide wheel. Hang on. I take it back. This is a silicon carbide wheel, but here's two silicon carbide wheels. This one is a 100 grit silicon carbide wheel. So silicon carbide is a different chemical, okay, from aluminum oxide. And we had a discussion yesterday. One of our community was talking about trying to make ground stones using a silicon carbide wheel. Because if you read about it, you'll learn that silicon carbide is harder than aluminum oxide. That's true. It's not enough information. So we'll talk about that. Silicon carbide is a little bit harder than aluminum oxide is. But more importantly, the grain is a different shape. So let's do a little thought experiment. If I said to you, you're going to carry a knife around for general purpose cutting, what material would you like that knife to be made out of? How about steel? Is steel a good choice? Okay. But what if I told you I could make you a blade out of glass that's going to have an edge that's 10 times sharper than the steel knife that you have in your pocket? Would you change to carrying around a knife with a glass blade? Yeah, CPM S35VN. Thank you. That's a knife steel. Okay. So answer in the chat, would you carry around a pocket knife with a glass blade? Sir Henry says what he doesn't like is the fact that there are multiple standards for grit sizes. Absolutely. I totally understand. I believe everything we're talking about is ANSI. And sometimes you have to make the jump. So I apologize. I'm going to stick to these numbers, which I believe are ANSI. So your mileage may vary. Ugly Skull says, nope, he would not carry around a glass-bladed knife in his everyday carry. Ugly Skull, why not? Somebody tell me why you wouldn't carry around a glass blade. Or somebody tell me that you would carry around a glass blade. While you're typing that, I will tell you that some of our biologist friends who do microscopy and slice very thin layers of biomaterial to put under a microscope, they are using glass blades. Ugly Skull says it's sharp but too brittle. Everybody say it with me together. The glass is sharp, but it's too brittle. Indiana John says it a different way. He says there's no flexibility. Nice. Nick says no glass blade and no tungsten carbide blade either. Why? Because it will snap, it will crack, it's too brittle. We all have this intuitive understanding of why we are carrying a steel blade and we're not carrying a glass blade. Can we agree on that? I think we could agree on that. So let me stick something in your head, okay? Steel blade, glass blade. So the silicon carbide is analogous to the glass. Foxberg says wrong viscosity glass. Oh, Oh, Foxberg says Engineer's Black Book also has a decent general wheel nomenclature breakdown on page 157. If you have Engineer's Black Book, open to page 157 with me, okay? Hey, Proteum, welcome aboard. So if we go down to the microscopic level and we look at the silicon carbide grain, aluminum oxide grain, the aluminum oxide grain is tougher. It's a little smoother, okay, but it's much more rugged. That one little piece of rock made out of aluminum oxide. If you look at the silicon carbide grain, it will be much sharper, but it will also be very brittle, which comes with being harder. Hardness, brittleness. I think we understand that. Okay, so is there a time when you want harder and brittleness comes along with it? The answer is yes. So why would you want something that's harder and sharper? Think about that. If I'm going to and some of it's non-obvious, okay? So silicon carbide, I could walk up to a piece of glass and I can grind glass with silicon carbide. I could grind tungsten carbide with silicon carbide. Also, silicon carbide can do something else that's very interesting. If you're going to grind aluminum, and believe it or not, there are applications for grinding aluminum, you do not want to attempt to do that with aluminum oxide. There's chemical reasons right at the very hot zone of grinding where your aluminum oxide and your aluminum making more aluminum oxide, they kind of like each other, and all of a sudden you have a chemical reaction. Whereas silicon carbide will not have that chemical reaction. The same reason you wouldn't grind steel with diamond, because diamond is made up of what element? Carbon. Oh, that's a really good point. Ugly Skull says, if I'm cutting something that's really delicate, I think I want the least resistance. So you would want a really sharp blade for a cutter. The more delicate it is, that sounds like silicon carbide, doesn't it? Okay, so that's a major difference between the two. T. Sanchez Moraes says, AL203. That's the stuff. That's our friend right here. So those are some of the reasons that you choose one over the other. Aluminum oxide versus silicon carbide. So that's on the microscopic level, when we look at that little piece of grit. So right now we could talk about three little pieces of grit: aluminum oxide, silicon carbide, and we talked about diamond. And of those, that's the order of hardness. Aluminum oxide has a certain hardness. Silicon carbide is harder. Diamond is way harder. We talked a little bit about chemical stuff. Aluminum oxide, grinding aluminum in the hot zone, there's going to be some chemical reaction going on there we don't want. On the other hand, diamond, grinding steel, is going to cause another chemical reaction we don't want. So the diamond's made of carbon, and the steel is like a sponge for carbon. That's how we make steel, is we put carbon in it. And again, you get into the hot zone, and now it's like, give me your carbon. I want your carbon. And the carbon wants to dissolve into the diamond. I'm sorry, from the diamond into the steel, and you literally are yanking diamonds out of your wheel, and it doesn't work. So what do we do about that? We want something really hard for a real hard steel, but we don't want to use silicon carbide for reasons we'll talk about in a minute. So there's another thing called CBN, cubic boron nitride. Cubic boron nitride is really super good because it doesn't have carbon in it. And it's not getting its carbon dissolving into the steel. So you could grind steel with CBN, and there may be reasons you want to do that. Indiana John asks, are ruby wheels essentially aluminum oxide? Hang on. I like to have a visual, and I don't want to drop any on the floor. Is this the one you're talking about, Indiana John? The beautiful Radiac ruby wheel, which, so no, they're not essentially aluminum oxide. They're exactly aluminum oxide. So it's aluminum oxide. Okay. Sometimes you have aluminum oxide with a little bit of spice in it, but it's basically aluminum oxide. So we talked about, go back to our 1947 chart, okay? We talked about abrasive types and at the microscopic level, why you might want one over the other. Just like if I was milling, you know, a piece of steel, like I was on the Bridgeport on Friday and I was using a carbide tool, but my travel speed was kind of slow because I was on the Bridgeport and I was making these little needles. I probably would have been better off with a high-speed steel tool going slower. Again, you make that choice. So that's type of abrasive. We already talked about the size of the abrasive, which matters the least of all of these. And then there's this thing they call grade, okay? This is where it gets a little funky and it starts getting complicated. So you got these grits that are gonna do your cutting, okay? How do you stick them all together? Ah, yes. Kevin Blodgett says, is the diamond steel interaction only a problem on powered operations? For example, sharpening a blade by hand with a diamond hone. Excellent question. The answer is generally yes, you are correct. Because remember, we kept talking about the hot zone, the high temperature zone. Because I use a diamond sharpening plate in the kitchen, and when you're sharpening by hand, you're not hitting those temperatures. So you're not hitting the high temperatures where the carbon wants to dissolve into the steel, right? That's the magic, is you're being nice and slow. In fact, I don't want to grab it, but literally 24 inches that way is a Glendo lapping machine, which has a diamond plate, and it's moving literally 200 RPM, and you could put high-speed steel on that all day long. It's about the heat. Okay. Excellent point. Thank you for bringing it up. So how do you hold all these grits together? The V, if we go back to our wheel, right? 38A, 46, H, and then there's a V. The V stands for vitrified. That's like the melting of glass is like vitrification. So there's this process where you're using some more spice in the mix, and you bring it up to a high temperature, and the spice kind of melts, and it holds all the grains together. So, you know, you go make sugar cookies, right? What's holding all the flour together? It's the sugar. The sugar is going in there, and then it's drying out and crystallizing, and it's holding everything together. So now when you look at this wheel, I don't want you to see aluminum oxide. I want you to see aluminum oxide with a binder. There's something holding the aluminum oxide together. And that is, it could be holding it together very strongly, or it could be holding it together very weakly. And Norton calls this grade, and it literally goes from A to Z, okay? And the most common ones, by the way, there's a little trivia. If you read up on the old stuff, you find out that originally M would be the medium. So it started with like low, medium, high, and then eventually they decided that no, M is a letter in the alphabet, and then they go super soft to A and super hard to Z. Now they call it soft and hard. Don't blame me. It should be called, more friable and less friable. Friable means it can get ripped apart. More friable means it's very strong. Less friable, I'm sorry, it's the other way around. More friable means it's weak. Less friable means it's strong. Okay, but that's where the grade comes from. So if we go back to Baby's first wheel, this one is an H, 46H. It's just right. It's nice, okay? It's a good place to start. But you can go up to a J if you want it harder, like you're doing form grinding and you want your form to hold, or you could drop it back down to an I. Like I have some I wheels that are a little softer. So you have to be a little careful in using the soft and hard designation, even though it's used throughout, the industry. You're not really talking about a material being soft and a material being hard. You're talking about the binding agent of the wheel. If it's hard, that binding agent is very strong. And if it's soft, that binding agent is kind of weak. So why would you want a wheel that is holding its grains really hard or not so hard? Does anybody know? There could be, Sir Henry says V, as in Victor, would be in Germany a ceramic binding. Yeah, so the old Norton designation is V for vitrified, S for silicate, B for resinoid, or it uses resin, R for rubber, and E for shellac. That's not used anymore. And O for magnesite. I don't have any clue what that means. And nowadays we have some really cool wheels that have other binding agents. There's one I have here called seeded gel. I have no idea. It's the Norton 5SG wheel. I have not studied it, but that's where the magic is. So Foxburst says loading of the wheel versus breakdown. Excellent. And Indiana John says, is it depth of cut related? Good thinking. And Toolmaker 365 summarizes it really nicely. As grains are removed, new sharp cutting edges are exposed. So it's a combination of all of these things. Sometimes you'll have a wheel that burns, okay? It's happened to me, especially on soft steel, where it literally burns the steel. You see these blue streaks on the steel, and those grains are holding on. They don't want to give it up. Well, those grains might have gotten dull, just like a knife blade, and now they're literally rubbing on the steel, and they're burning the steel instead of grinding the steel, which is a cutting process. So if you softened up your hold on those grains so that when the friction goes up, because they're not cutting anymore, they pop off and they go flying and they expose fresh grains, now you're cutting again. So there's this balance. It's like, well, I don't want my wheel to break down because I want my size to be perfect. That's nice, but your wheel's going to get dull and you're going to have to dress it. Or you could soften up your wheel, and those grains will go away when they get dull, exposing fresh grains. That's the trade-off, and that's why we go to a more friable and a less friable wheel. Now, in my experience, well, let's just hold there for a minute. Does that all make sense? That's the grade of the wheel. And if you have had an experience with burning when you're grinding, this is what's happening. Okay, maybe you go to a softer wheel. Maybe you literally need to dress your wheel. But those are the solutions. And what is dressing your wheel? Dressing your wheel is running a diamond across your aluminum oxide wheel and knocking out grains, getting rid of grains, and reforming that face. Okay? So if that process becomes automatic, the process becomes smoother. Holding dimension might be harder. Trade-offs. Okay? Are there any questions so far? All right, so we talked about hardness. We talked about friability. Let me give you another hardness question. When we talk about how hard a material is, we're talking about how hard a material is sitting on your bench or sitting under your microscope. Okay? So we have a grain of sand, which is possibly a silicate. We have a grain of aluminum oxide, which came out of my grinding wheel. We have a grain of silicone carbide, which came out of our grinding wheel, and we measured them and said, yes, this is harder than this. Then, has anybody ever seen a water jet cutting without garnet, just with water? Almost Machining says it doesn't. He's referring to dressing. Dressing doesn't always knock out the grain. It can also shear them off, related to dressing speed. Excellent. Yeah, so is water hard? I thought water was soft. So how can you cut with water? Tuck Garage says he has cut selenium, ZN, that's zinc selenide, with and without garnet, and it will only cut with garnet. And Indiana John says it depends how fast it's moving. Right. So in water jet cutting, the water is moving so fast that it behaves hard. Now, our grinding wheels also are moving pretty fast, and one of the things you learn in the grinding lore is that if you want a wheel to act harder, you can spin it faster. And that's kind of starting to sound the same, doesn't it? Surge Creator just joined us. Welcome. Anyway, the other thing I want you to think about is, as you're driving to dinner tonight on a nice paved road, I want you to look down at the road when you stopped and parked, okay, and look at the asphalt. What is the asphalt? The asphalt is made out of gravel, rocks, in a oil-based asphalt binder. Does that not sound like a grinding wheel? Because it sounds like a grinding wheel to me. So when the civil engineers designed the roads, they made a composite which is very much like our grinding wheels. It's got some little hard things, and it's in a bed of kind of soft stuff. And it gives it the properties you want. It gives it wear properties from the hard things, and it gives it the ability to be flexible from the soft things. isn't that the grains in our wheel and the binder in our wheel being independently engineered? Foxberg says it was a grinding scenario when I was a kid on a skateboard. Absolutely. Yeah, you don't have to explain to any kid with a skin knee that the asphalt is also a grinding wheel. That's pretty logical. That's pretty funny. Okay. Next on the list is this thing called structure. Let me read you what it says inside this box. It says the structure of a wheel refers to the relative spacing of the grains of abrasive. It is designated by a number. The larger the number, the wider the grain spacing. Okay, so if you just pick up a wheel and look at it, like here's my silicon carbide wheel. That won't focus. Thank you. That looks real dense, and it is. This is a 100 grain silicon carbide wheel, 100 grit, sorry. And you can't see the space between the grains. If you pick up our aluminum oxide 46H here, baby's first wheel, you actually could start to see spaces between the grains with your regular eyeball, okay? And then we pick up some other interesting wheels like this beautiful Radiac RA60H800, and look at that sucker. Okay, you could, a colony of ants can live inside this wheel. Is that not gorgeous? Look at that on YouTube. Okay, way open structure. Okay, and then there's another old Norton wheel here. Well, it's actually two of them. This one is labeled 32A 46-G12. And look at that open structure. Kind of the same. It looks like about the same open structure as our Radiac. This one, however, is ancient. This one is current. You can go buy this right now. So now we have structure. So we've got our rocks, we've got our asphalt. Now we're looking at the potholes. So in our world, what value does the potholes have? Why do we want to have potholes on our road? A lot of people complain about the potholes on the road, and here we are literally building in potholes on the road. Why do we do that? Foxberg's fabric hobbling says heat. I like that. Sir Henry says wider spacing is for roughing, if I'm right. Toolmaker 365 says for cooling. Indiana John says less loading up. Almost Machining says heat. So the only one I'll disagree with is the roughing question. Although you could make your argument that that's also legitimate. So there's a couple of reasons. Number one, if the swarf has a place to go, we talk about this on PFG Stones with the so-called coarse grit. If the swarf, coolant versus dry. If the swarf has a place to go, it gets out of the way, and it doesn't load up. Loading up, of course, leads to heat, and it's starting to rub instead of cut. All of these things are true. So those holes give the swarf a place to go. But also, if you're using coolant, there's a place for the coolant. It just started pouring here. There's a place for the coolant to go, and the wheel is carrying more coolant. Another reason it stays cool. So if you're using coolant, the open structure will stay cooler. If you're not using coolant, the open structure, it actually, there's less cutting happening per revolution, which leads to lower temperatures. So there's all of these things play into this, but that is one of the reasons we like potholes in our road, right? So we take our rocks and we put them in asphalt, and then we put intentional potholes in it. Yeah, almost machining. Brilliant point. So, yeah, Sir Henry says still learning about grinding. We're all still learning about grinding. That's not going to stop, by the way. Almost brings up a good point. If you have heat buildup, okay, your part grows, and it's going to grow into the wheel. What's that going to cause? More heat buildup. So it's a positive feedback problem. Okay, so if you, and I guarantee you as a beginner, you will learn this in grinding the chuck, because you're grinding soft materials and they really want to load up. And as soon as they load up, they're making heat and bad things start happening. Okay. Almost points out that it could be dangerous. It could be a safety issue. And that is also true. So now you know something about why we choose the different structures, okay? And why we would want an open structure versus a tight structure. Are there any questions? If any of you guys are woodworkers, or even, you don't have to be a woodworker, but I think woodworkers would be more familiar with it. You could buy sandpaper, which is sand, literally aluminum oxide or silicates on paper. Then you could buy the good stuff, right? The good stuff, the wet dry, which is on a special paper. Then you could buy the cloth backed sandpaper. Then you could buy the screen sandpaper. Aren't we talking about the same stuff? Isn't this all the same? It's all the same. So there's no, the mystery is it's not like in front of your face. It's not obvious. But now, hopefully, with these analogies, you'll go and look at a grinding wheel and start to think differently, and this stuff will cease to be a mystery. If you've ever been in Hawaii, when I was there years and years ago, we learned about two different kinds of lava that the locals had named. Does anybody know the two basic types of lava? And I couldn't find a really good picture to show you, so I'll try to do that for the future. Anybody know about the two basic types of lava? Anybody here from Hawaii? I don't think so. I'll take a sip of tea while you think about that. Kevin says buffing wheels are the same, just different materials. Absolutely. Molten and cooled. Those are two types. I will give you that. That's not what I had in mind. The goopy and the running. Yeah. So you've probably seen pictures of lava flowing, and then when it cools off, you see these really smooth kind of structures. That was the flow that then froze. And that smooth kind of lava is called Pahoehoe. And there's other kinds of lava that looks like a gravel field, but each piece of lava is this incredibly sharp thing that is just sharp points everywhere with lots of holes. It's very reminiscent of the open structure of the grinding wheels that we were just looking at. And that lava is called ah. So you got ah, which is the real sharp pieces, and then you got Pahoehoe, which is the smooth pieces. And the name Ah is easy to remember. Oh, Indiana John says one is glassy and the other tarry. I don't think I know that word, but I think we're communicating here. So when you think about aluminum oxide grit, think about Pahoehoe. Okay, it's not super sharp, but it's tough. And when you think about silicon carbide grit, think about oh, tar-like. Yeah, no, one is sharp and one is smooth. One is kind of smooth, and one is super sharp. I had samples of each, which I gave to a friend, and he couldn't put his hands on it quick enough. When he finds it, because he's unloading his basement. When he finds it, we'll get some good pictures of it. But if you look it up in the dictionary, you'll see it. We didn't talk a lot about diamonds, and you might think, well, diamonds, why don't we do all of our grinding with diamonds? So, well, number one, they're hard to work with because they're hard, and they're more expensive. They're not crazy more expensive. Industrial diamond grit is not like, wacky expensive, but it's more expensive. Holding the diamonds is a challenge, and the most common way of holding diamonds. Let me grab a diamond wheel. This diamond wheel is sporting a B200 balancing ring from Kinetic Precision. Need balancing? Go to bal.gg. Yes, this was a commercial. This is a diamond wheel. This is a resin bonded diamond wheel. So our diamonds, focus. Our diamonds are in a soup of resin. This is my coarsest diamond wheel. You could actually feel it. This is 100 grit diamond wheel. So now let's think about this for a second. This is aluminum oxide. This is diamond. Which is harder? Diamond is harder than aluminum oxide. This is a vitrified wheel. This is a resin bonded wheel. Which of the binders is harder? Vitrified is harder and tougher, well, I'll say harder, than the resin. So it's a very different animal. And Kevin Blodgett wants to remind me, because he was there on drums, I played bass for Soup of Resin back in the 80s. So as soon as you start to hold these real hard things and this real soft stuff, it becomes a different deal. Almost Machining says something. I like this. Almost Machining says you can use wheel X on material Y. There are just limitations. Once you reach a condition that doesn't seem correct, the wheel is what needs to be changed or dressed. I like that. That's a great summary statement. All right, we're going into the weeds here. So if we look at our Norton chart, which of course this was not really intended to discuss. Well, I guess is diamond on here? No, it isn't. So diamond, right? Diamond's the abrasive. The grain size is, this case is 100 grit. The grade, right? The resin. I don't know that there's generally a designation for the behavior of the resin. The structure, there's no structure. We don't have a lot of choices there. And the bond is resinoid, which is one of our choices. It becomes a different animal, which I think is beyond the scope of today's discussion. I don't think I want to go off into the diamond wheel weeds. We'll leave that for another day. But now I think you have a mental picture of the grits, the grit sizes, what what the grade or the friability means, what the bond means, and what the structure means. And then all of those variables are what you get to play with. You can always you can always use a less optimal wheel to get the job done. If you slow down, take lower cuts, add coolant, there's things you can do. Just like on the milling machine, you don't have a carbide cutter, you can use a high-speed cutter. You just have to make adjustments. But I hope for somebody, some of the mystery was taken away from, you know, all of these zillions of combinations of grinding wheels. If you are going out to buy a grinding wheel to use, you know, get yourself something like this, a basic grinding wheel. If you end up getting a super great deal on some really fancy grinding wheel, fine. You're going to learn something new, and you just may have to change your order of operations. The last thing I'm going to leave you with on the whole grinding wheel thing is, hang on. I had to get another prop. Especially for beginning grinder guys, we tend to like cherish our grinding wheels. This is the equivalent in the shop of this. Okay? You use them up, you throw them out, you get another one. This is, you know, 15, 20 bucks. All right? It lasts you a couple of months. It's gone. You use it up, get another one. You do not have to treat these like gems. You use them up. They are a consumable. You can, in fact, they kind of look alike, don't they? You consume them and you use them. With that, I will stop blathering about grinding wheels. I hope somebody got some mental pictures that can help you in understanding how all this stuff works and how to move forward. So at this point, Paul Morley says, I got a zillion wheels in the mail this week from Mr. Foxburg. That's excellent. Almost Machining says, next week, carbide grade chart. Yeah, we got a ways to go. Oh, a question came in. Okay, let's break down this question. Ugly Skull asks, with different materials used on grinding wheels, is there some sort of pressure applied on the material being ground? If I constructed my question right. So the really super nice thing about the grinding process is that the pressures involved are actually really low. You know, that's why we could throw something on a magnetic chuck with very light, you know, magnetism, and there's not a lot of pressures involved. On the microscopic scale, you have little teeny areas of pressure which could lead to things like burning, but only if you make a mistake do you have significant pressures which can, for example, throw apart. Okay, it's not like it shouldn't be like milling. Okay, that those pressures are very light. I hope that makes sense. Is there without pressure, there's no cutting, but things are happening on such a microscopic scale that the actual pressures are not very high. Did I answer that question? I think. I hope. Almost Machining says, we used to use 2-inch by 4-inch by 8-inch 46 grit size segments on a Blanchard with a 75 horsepower motor on it. That's awesome. What kind of wheel for form grinding? I don't know how far and wide the materials go, but if you're going to cut a form in a wheel, generally I've seen the good old white wheel used for form cutting, and then you'll go to um, a harder grade or a less friable wheel to hold your form better. But basically, again, you could go a long time with depending on your materials, of course, with baby's first wheel to do a lot of stuff, and form grinding is one of them. And I haven't done a lot of form grinding, and my machine is made for custom form grinding, and I haven't really gotten into it very much. Almost Machining says, don't grind with an electromag or a electric magnetic chuck during a thunderstorm, because if you lose power, you lose hold down force. Clay Bond for finish form grinding. You're out of my league. I don't know anything about Clay Bond, although I think he owes me $20. All right, guys. So we went over today. Thank you for hanging in there. I hope this was useful. I hope that you know why you're not going to go out and use a silicon carbide wheel to grind aluminum oxide stones, and maybe you're starting to understand why that's such a pain in the ankle. And maybe you have enough information to start, playing with your grinder more. Last questions, and then we're going to close this sucker up. You're welcome, Kevin. Again, I am a student. I'm just passing along the things that started to make sense to me over the last 5 years. Nick says the other day he found out that the E-stop on the grinder also turns off the chuck. Yep. Thank goodness for residual magnetism. 100J. I'm not sure. Oh, is that the wheel? 100J. Wow. A lot of dressing. Yep. Yeah, no. If you're worried about putting your mag chuck on a UPS, I'm going to say you're doing it wrong. The probability that you're going to end up in that situation is low. Thanks, Joel. Thank you, Almost. Thanks for being here, man. And Lewis Younger, welcome aboard. We're just wrapping up. I'm sorry. All right, so this will be on YouTube at Kinetic Precision NH, and this will be also on Instagram in the usual places. Stay tuned. We're going to have an Instagram. We're going to have a YouTube only session coming up sometime in the next few weeks, so that we could have a guest and do some proper guest interview, and it'll be on YouTube. Have a great day, everybody. Go enjoy your day. If you're in the Northeast, stay cool. And if you're in Porto, try the port. See you later.